In this video, we're going to look at an example problem using the model we derived in the previous video for the photoelectric effect. So let's look at this problem. It says that the work function for metallic cesium is 2.14 electron volts, EV. It's got two parts. So it says A, calculate the maximum kinetic energy of the electrons ejected by light of wavelength 700 nanometers. Would an electron be ejected in this case? And B, it says calculate the speed of the electrons ejected by light of wavelength 300 nanometers. Okay, so right off the bat, we know we're going to have to use the equation that we looked at in the previous video, where the kinetic energy of the ejected photoelectron is going to be equal to h nu minus the work function. Right, so we know that in each of these cases, there's going to be light impinging on the cesium surface, and we're trying to figure out, is there going to be a photoelectron ejected? And if so, what's its speed? What's its kinetic energy? We want to know more information about it. So right off the bat, if you're asked a question like this, the first thing you want to do is convert everything to SI units, right? You want to convert everything to your base SI units. It just makes everything easier for cancellation at the end. Obviously, you don't have to do this. If you want to convert at the end, that's fine. But I think it's a lot easier to keep track of everything if you just, from the beginning, convert everything to your base SI units, right? So we're going to need a few conversions for that, right? So 1 electron volt is going to be equal to 1.602 times 10 to the negative 19 joules. And for nanometers, 1 nanometer is equal to 1 times 10 to the negative 9 meters, right? So we're going to need these two conversions definitely, right? We want to convert that work function from EV to joules, and we want to convert all of the wavelengths of light that we have from nanometers to meters, right? So we're going to need to use these two conversions. Also, we want to write out all of the constants that we know we'll need, right? So we know we'll need Planck's constant, right? So Planck's constant is 6.626 times 10 to the negative 34 joules times seconds, right? So you know you're going to need Planck's constant in this. So it's good to have that ready and to convert all your energies to joules so it'll be compatible with Planck's constant and its units. Right, we'll need the speed of light. That's going to be 2.9979 times 10 to the 8 meters per second. Some people just say 3.3 times 10 to the 8 meters per second. That's fine as well. I like to carry those few other decimal places along with it. We'll also need the mass of an electron. And the mass of an electron is 9.109 times 10 to the negative 31 kilograms, right? Again, SI units, right? And for joules, I just want to note that in SI units, joules is kilograms meters squared per second squared. Okay, so we got all the constants that we need. We have conversions that we need. A little reminder about joules in SI units. So let's start doing some work here. So the first thing I want to do is convert convert the energies and wavelengths to SI units. So I want to convert everything to SI units. Right, so let's start with the work function. So the work function that we've been given here for cesium is 2.14 EV. Right, so if we want to convert that using this conversion factor, then we get 3.428 times 10 to the negative 19 joules. Okay, and for our wavelength, for part A at least, our wavelength here, we're given a wavelength of 700 nanometers. Using the conversion factor up top, we get 7.0 times 10 to the negative 7 meters. Right, so we've converted for part A the wavelength to meters. We've converted the work function to joules, right? So now part A is asking us would an electron be ejected from the metal in this case, right? We saw in the previous video that if the impending radiation has less energy than the work function, an electron would not be ejected, right? So we saw that if h nu is less than the work function, then we wouldn't get a photoelectron, right? There will be no ejection. So what we need to do here is calculate h nu and then compare it to the work function and first see if a photoelectron will be ejected at all, right? So let's do that. So if we're calculating the energy of the photon, so we want to calculate photon energy. Right, so h nu, if we plug in the expression for the frequency is just going to be the speed of light over lambda, right? We can plug that in and this becomes hc over lambda, right? And so if we plug in everything here, right, we plug in our Planck's constant, speed of light, and the wavelength of 7.0 times 10 to the negative 7, then we get an energy for our photon of 2.838 times 10 to the negative 19 joules. Right, so this is the energy of our photon right here. If we compare that to our work function, what you'll notice is that the work function is actually greater than the energy of our impending radiation. So that means we would get no electron ejected here, right? No electron ejected. Right, so the answer to this one is that there is no maximum kinetic energy because there's no kinetic energy in the first place. The electron would not be ejected from the cesium surface. So that's the answer to part A. So this is a check that you'll always want to do. Now, if you were to just plug this into this equation anyway, let's say you just calculated the kinetic energy. If you get a negative kinetic energy, that means that no photoelectron is ejected. So you can do either or. You can calculate the energy of your photon, compare it to the work function, see if a photoelectron will be ejected, or you can just plug it straight into this equation. If you get a negative number, right, that means this work function is greater than h nu. So there's no photoelectron in that case either. Okay, so let's do part B. Part B is asking us to calculate the speed of the electrons ejected by light of wavelength 300 nanometers, right? So similar to the first one, let's do the conversion first. So I'll convert here. If we have 300 nanometers, right, in meters, that would be 3.0 times 10 to the negative 7 meters. So we're going to use that for to calculate the speed of this ejected electron. So let's do it. Let's go to a new slide here. Okay, so we want to plug in to this equation, right? We got kinetic energy is equal to h nu minus the work function, phi. So plugging in here, we get the kinetic energy is equal to, right, we want hc over lambda since we're given a wavelength. Right, now we're ready to plug in. So we know Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Speed of light, 2.9979 times 10 to the 8 meters per second. Over the wavelength, which is 3.0 times 10 to the negative 7 meters, minus our work function for cesium, which we calculated on the previous slide, which is 3.428 times 10 to the negative 19 joules. Okay, so looking at our units here, just making sure we check everything out so it makes sense. Meters cancels here, seconds cancel here. right? So we're just left with joules. So these are compatible units. And so from this calculation, you get a kinetic energy of 3.1934 times 10 to the negative 19 joules. Okay, so now that we have the kinetic energy, we can use that kinetic energy to calculate the speed of the ejected electron. Keep in mind, that's what we're looking for here in part B. We want to calculate the speed of the electron, right? So we have the kinetic energy, we can use that to calculate the speed, right? So we just substitute 1/2 mv squared in here, right? So let me actually just use symbols here. So we know that the kinetic energy is equal to 1/2 mv squared. Right? So doing some algebra here, you get that the velocity is going to be equal to 2 times the kinetic energy over the mass. And this mass is going to be the mass of the electron, right? So when you plug in everything here, right, you're going to get 2 times 3.1934 times 10 to the negative 19 joules over the mass of the electron, which is 9.109 times 10 to the negative 31 kilograms, right? So when you do the units, right? So keep in mind, if you look at joules and SI units, it's kilograms, meters squared per second squared, right? So when you do the units here, this direct cancellation should give you meters squared per second squared. You square root that, you get meters per second, right? So the final answer here would be 837,343.609 meters per second, right? So that would be the speed of our ejected photoelectron. So keep in mind what we did here, right? So we used the work function, right? We used the photoelectric effect equation here to calculate the kinetic energy first. Using that kinetic energy, we were able to calculate the speed of the ejected photoelectron. So this equation is pretty routine to use, right? Like I said, my best general tip for these types of problems is, write down all of your, constants, or if you're using an Excel sheet, go ahead and plug them in and do all the conversions, put everything in SI units so that when you get down to an expression like this, right, you're not confused. You're not sitting here with a work function in EV and a mass in kilograms and wondering what you should do, right? If you put everything in SI units, then the cancellation more or less takes care of itself.